Yes, I am Raghavan, chemistry faculty from All Fours College. I welcome you all for the All Fours Chemistry e-learning program, session 20. Okay, in this session, let us work out some numericals on de Broglie theory. Okay, in the last session, that is in the session 19th, yesterday we completed the de Broglie concept of de Broglies, that is derivation of the de Broglies theory and significance of the de Broglies theory we have done. Okay, significance of de Broglies is completed. Okay, so before going to take up the numericals, we have some more concept, that is, yes, that is important also. Okay, let us find Bohr's theory and de Broglie's concept, de Broglie concept and Bohr's theory. Okay, so that is de Broglie's theory and Bohr's concept, they are in very good agreement with each other. So that point we have to observe now. So that is, according to Bohr's theory, electron is revolving around the nucleus in closed stationary orbits. That means as long as electron is revolving around the nucleus, it neither loses energy nor gains energy. That means energy of the electron in the orbit is constant. Okay, that is why orbit is called stationary orbit. We called it as energy level. Okay, now according to de Broglie, electron is propagating in the form of wave. So now according to Bohr, it is a stationary orbit. According to de Broglie, now it should be a stationary wave. We have to see that the wave, it is electron wave is a stationary wave or non-stationary wave. That point we have to observe. So now the first condition let us observe, that is the circumference of the Bohr's orbit 2 pi r is equal to integral multiple of de Broglie's wavelength. It is integral multiple of de Broglie's wavelength. Okay, what is the first condition we are taking? The circumference of Bohr's orbit when it is equal to integral multiple of de Broglie's wavelength. Okay, now lambda is equals to h by mv, that is according to de Broglie. So now 2 pi r is equals to n into h by mv. Okay, h by mv. Now rearranging the terms. Okay, it is 2 pi r. So now mvr is equals to nh by 2 pi. So this is the de Broglie theory and this is the Bohr's theory. So that means the Bohr's theory is in good agreement with de Broglie's theory. Okay, so that's we can understand from this. Okay, right. So now according to Bohr's theory, electron is revolving around the nucleus. Is it a closed orbit? No, it is not a closed orbit because the two ends of the circle does not meet. So if two ends of the circle meet, what happens? The electron continuously passes in the same circular motion. As long as it revolves around the nucleus, it neither loses energy nor gains energy. Therefore, we already described that the circular orbit according to Bohr is a stationary orbit. Okay, that point we know that. Okay, that is according to Bohr, the orbit is stationary orbit. Okay, now the same concept now we are observing, we are experiencing according to the de Broglie's theory. Now according to de Broglie, this point, this is electron is propagating in the form of wave. Okay, now according to de Broglie, electron behaves like a wave. Now let us see, this electron is propagating in the form of wave. The electron is propagating in the form of wave. Is propagating in the form of wave. Okay, right, done. So how many waves are there in this? 6. 1, 2, 3, 4, 5, 6. So that is, it is 6th orbit, n is equals to 6. The number of waves made by the electron in 6th orbit is equal to n, orbit number only. So it is in number, that is in 6th orbit we have electron makes 6 waves. Okay, fine. Now the condition, the circumference of the Bohr's orbit is equal to the integral multiples of de Broglie's wavelength. Okay, understood. Now when, see for example, the two ends of the electron wave does not meet. So now it does not meet. So that means it is not a continuous wave. Okay, when two ends of the electron wave meet, when the two ends of the electron wave meet, what happens? The electron continuously passes in the same wave motion. Now once again the condition, when circumference of the Bohr's orbit is equal to the integral multiple of de Broglie's wavelength. Okay, in that condition, how we are describing that? Observe. When two ends of the electron wave meet, when two ends of the electron wave meet, electron continuously passes in the same wave motion, forming the regular number of crusts and troughs. It forms a regular number, that means same number of crusts and troughs. As long as electron is revolving in the same loop, that is same wave motion, it forms the same number of crusts and troughs. Such electron wave is called non-stationary wave, is called non-stationary wave. Okay, non-stationary wave, sorry, it is stationary wave. It is stationary wave. Okay, it is called stationary wave. And so during this, when electron is revolving in this same wave motion, it neither loses energy nor gains energy. Therefore, the energy of the electron in the wave motion remains constant. Therefore, it is called non-radiating wave. It is non-radiating. That means it is not going to emit any amount of energy. So therefore, it is called non-radiating wave, or it is called stationary wave, because the energy of the electron in that wave path is constant. Okay, that is stationary wave, or it is called non-radiating wave. Okay, R. Okay, R. So all this nothing but R. Stationary wave R, non-radiating wave R. The electron is said to be in phase. Electron is said to be in phase. Electron is said to be in phase. It's not out of phase. The electron is said to be in phase. Okay, the electron is said to be in phase. Okay. Next, it is forming the same regular number of crusts and troughs. So therefore, it is called, such wave is also called constructive interference wave. What is that? Or it is also called constructive interference wave. It is also called constructive interference wave. Constructive interference wave. Okay, stationary wave or non-radiating wave, or electron is said to be in phase, or constructive interference wave. Okay, so this is the condition for this, for which the circumference of the Bohr's orbit is equal to integral multiple of de Broglie's wavelength, where the angular momentum of the Bohr's theory is in a good, that is MVR is equals to integral multiple of de Broglie's wavelength. Okay, that is integral multiples of, that is n lambda, de Broglie's wavelength. That means the de Broglie's wavelength we can find it out, that is n into h by mv. Okay, so this is like this, integral multiple of de Broglie's wavelength, right? So this is one condition. That is, what is that? According to Bohr's theory, electron is revolving around the nucleus in circular orbits. That circular orbit is called stationary orbit, okay, or energy level. That means as long as the electron is revolving in the circular path, that is in the circular orbit, it neither loses energy nor gains energy. So we know that orbit is stationary, energy is constant in that. Now similarly, so that is according to Bohr. According to de Broglie, now we are applying the concept of de Broglie in this orbit, okay. So when electron is revolving in the certain orbit, say for example n is equals to 6. So in that orbit, electron is propagating, it is revolving, it is propagating in the form of wave. How many waves it makes? It makes the same number as orbit. So it is 6 waves it makes, okay, very good. So now, in this, when it is moving in the circular orbit, that is in the form of wave motion, when two ends of the electron wave meet in the path, the electron continuously passes in the same wave motion, forming same number of crests and troughs. Such wave is called stationary wave, okay. That point you should understand clearly. Stationary wave, okay. So is it during this moment, does it going to emit any radiation? No, it is not emitting any radiation. Therefore, it is called non-radiating wave, okay. That is called non-radiating wave, okay. Or the electron is not moving out of the phase, so therefore such wave is called, that is, such electron is said to be in phase, okay. Next, since the electron is forming the same number of crusts and troughs, so such wave, such electron is called constructive interference wave, because it is forming the same number of crusts and troughs, okay. So this is one condition, okay. Sir, suppose if the circumference of the Bohr's orbit 2 pi r is not equal to integral multiple of n lambda, okay. If that is the condition, then what we can take, okay. So that is the condition. Now it is, okay. I think the first condition, I think it is understood, okay. The first condition is done. Now coming to the second part, that is second condition. What is that second condition we are taking? The circumference of the Bohr's orbit, if it is not equal to integral multiple of de Broglie wavelength, then what happens? Say this is orbit, circular orbit, okay. In this circular orbit, now let us see the electron is moved away. So that means, so from this electron is coming in this way and it is entering into the same loop, it is propagating the same wave motion, and now the electron is jumped away from its path. So what is the condition? The circumference of the orbit is not equal to the integral multiple of de Broglie wavelength, okay. The electron entered into like this, and electron, finally it's not the two ends of the electron wave does not meet, so the electron is shifted from its path. So therefore such electron is called, the electron is said to be out of the phase. So when this is a condition, so now such electron wave is called, okay, it is called, that was stationary wave, now it is called non-stationary wave. The energy of the electron in the orbit is not constant, so it is non-stationary wave. Okay, non-stationary wave. So non-stationary wave, so when electron is jumping from its orbit, okay, it emits some amount of energy, so therefore it is called radiating wave. It is also called radiating wave. Very good. It is radiating wave because amount of energy, when electron is jumping from its original path, so it emits some amount of radiation, so therefore such wave is called radiating wave, okay. Then the electron is slipped away from its path, so therefore the electron is said to be out of phase. electron is said to be out of phase, okay, it is jumped from its path. So electron is said to be out of the phase. Then this electron, when it is moved away from the moved away from its original path, so then the electron is said to be out of phase, and it is called radiating wave, and it is a non-stationary wave. Its energy is not constant, so therefore it is non-stationary and it is radiating wave. The electron is said to be out of phase, and in this path the electron is not forming the same number of crusts and troughs. Therefore such wave is called destructive interference wave. Okay, constructive interference, destructive interference. Destructive interference wave. Okay, so what is the condition? When the circumference of the Bohr's orbit is not equal to integral multiples of de Broglie wavelength. So these are the conditions applied. So sometimes, very rare cases, you can expect numerical based on this. Okay. How many waves made by the electron in nth orbit? So the number of waves made by the electron in nth orbit, that is equal to n number. Okay, here once again I will write number of waves made by the electron in a given energy level, a given orbit is equal to n value, orbit. For example, if the electron is revolving in second orbit, how many waves it makes? N is equals to 2. That is why number of waves made by that electron in the second orbit is 2 only. Okay, one more example. How many waves made by the electron in third orbit? So third orbit means what? So in third orbit, orbit number is 3. So the number of waves made by the electron in the third orbit is also 3. Okay, like that. Okay, now the two conditions are satisfied in this. Okay, so when electron is said to be in phase, when electron is said to be out of the phase, the condition is the circumference of the Bohr's orbit is equal to the integral, because n is integer, integral multiple of de Broglie wavelength. Okay, so when this is the condition, so we can say finally the de Broglie's theory is in good agreement with Bohr's concept, but that is Bohr's theory. Okay, Bohr's theory and de Broglie concept. Bohr's theory and de Broglie concept both are in very good agreement with each other. It proves that. Okay, right. Okay. Now it is completed. Now let us see some numericals on de Broglie's theory. Okay. So numericals on de Broglie's theory. Numericals on de Broglie's theory. What are the numericals on de Broglie's theory? Okay, the numericals, that is de Broglie's equation is, yesterday we explained the de Broglie equation, that is, and relation between kinetic energy and de Broglie equation, that is de Broglie's wavelength. Okay, that we explained. Let us take directly numericals on de Broglie. Numericals on de Broglie. Numericals on de Broglie's, okay, concept. Now let us take one numerical. Okay, what is a numerical? How we can prepare that numerical? The de Broglie's wavelength of an electron. The de Broglie's wavelength of an electron. Okay. Let us prepare problem, that is question. Calculate de Broglie's wavelength. Calculate de Broglie's wavelength, lambda. Calculate de Broglie's wavelength of a ball of mass, say it is how much? 0.1 kg of mass, 0.1 kg, moving with velocity Okay, it is moving with velocity. Moving with velocity. So what is that velocity? Say it is, for example, 10 meters per second. Okay, moving with velocity 10 meters per second. Moving with velocity. With velocity 10 meters per second. Okay, calculate de Broglie's wavelength. Okay, that is the question. Now let us see. De Broglie's wavelength lambda is equals to h by mv. Lambda is equals to h by mv. Substitute the required data in this. Okay, lambda you are calculating. H is equals to Planck's constant 6.625 into 10 to the power minus 34. 10 to the power minus 34 joule second. And m is equals to mass of the electron. Mass of the ball. How much? 0.1 kg. 0.1 kg. So next, velocity v is equals to velocity of the ball. How much velocity it is moving? So with 10 meters per second. 10 meters per second. See here the point we should remember, that is all must be in the same units. Okay. So that is h. That is joule seconds SI units, and mass of the particle it is in kgs. Okay, and velocity in meters per second. Okay, it should not be in centimeter per second, it should be in meters per second. So all they are in the same units. So now substitute. Lambda is equals to, okay, that lambda is equals to 6.625 into 10 to the power minus 34 joule second by, okay, mass 0.1 kg. 0.1 kg into velocity, that is equals to 10 meters per second. Okay, that is equals to lambda is equals to 6.625 into 10 to the power minus 34 meters. That is the answer for this problem. Okay, so this is the basic format. Then we can calculate the de Broglie's wavelength like this. Okay, based on the given problem, so that we have to write the data first. Okay, based the data exactly we have to substitute. We should not change in the different units. Okay, next one more problem. Let us experience with one more problem. Okay, right. Next second, that is first question number 1. Now let us take question number 2. Okay, question number 2. Now let us start that question number 2. The mass of an electron is, okay, mass of an electron is 9.1 into 10 to the power minus 31 kg. Mass of an electron is 9.1 into 10 to the power minus 31 kg. Okay, and if the kinetic energy of the electron, if kinetic energy of electron is, okay, if kinetic energy of the electron is 3 into 10 to the power minus 3 into 10 to the power minus, okay, the kinetic energy of the electron is 3 into 10 to the power minus 25. That is, kinetic energy of the electron is 3 into 10 to the power minus 25 joules. Okay, calculate de Broglie's wavelength. Calculate de Broglie's wavelength of the electron. Calculate de Broglie's wavelength of the electron. Calculate de Broglie's wavelength of the electron. Okay, so like that we can calculate. Now let us take the data. What is that? That is mass of the electron. Mass of electron is equals to how much it is given? 9.1 into 10 to the power minus 31 kg. Yes, it is given. And next, kinetic energy of the electron, how much it is available? So that is 3 into 10 to the power minus 25 joules. Okay, done. It is also available. We have to calculate. Okay, lambda, find out. Lambda we have to calculate. Now, now from this, let us, in this kinetic energy formula is, kinetic energy is equals to Ke is equals to half mv square, half mv square. Now v square is equals to 2ke by m. Okay, or v is equals to under root 2ke by m. That is mass of the electron. Okay, now let us find out. Let us find out. So on substituting, or we can say instead of this, let us use okay, so calculate the, substitute and calculate the values of v, that is velocity of the electron. In the velocity of the electron, how much we can calculate in this? Velocity of the electron can be calculated as 812 meters per second. So substituting the values, that is 2 into kinetic energy, okay, by mass of the electron, and substituting that, so that is v square. Then now you are calculating v is equals to this much. Okay, so after calculating v, now you are calculating de Broglie's wavelength. De Broglie's wavelength, that is lambda is equals to h by mv. So therefore, that is, it is meters per second. H must be in 6.625 into 10 to the power minus 34 joule seconds by mass of the electron. How much it is given? Mass of the electron is available 9.1 into 10 to the power minus 31 kg into velocity. How much? 812 meters per second. Okay, so velocity is available. So on simplifying, on solving this, lambda is equals to, on solving this, the lambda is equals to 8967 into 10 to the power minus 10. Yes, into 10 to the power minus 10 meters. Okay, or that is equals to, okay, let us make it like this, 896.7 into 10 to the power minus 9 meters. As we know that 1 angstrom, 1 nanometer is equals to 10 to the power minus 9 meters, 1 nanometer. Therefore, it is equals to 896.7 nanometers. We can calculate like this. Okay, so in the given problem, what data is available first? So available data is just mass of the electron is available and kinetic energy of the electron is available. What we have to calculate? We are calculating lambda. Okay, once again let me explain this. So that is kinetic energy is equals to half mv square. So from this we are calculating v. Okay, v is equals to, that is v is equals to how much? How we'll get? That is 2 into ke by m. Okay, that is whole to the power 1 by 2. Okay, so from this we can calculate v is equals to 812 meters per second. Okay, you calculated velocity of the electron. Then after that, this velocity you are substituting in this. Okay, that is lambda is equals to h by mv. You are substituted and you calculated the lambda value as wavelength is equals to 896.7 nanometers. Okay, this is another numerical. That is, this type of numericals are very important for us for the objective examination. Okay, so we completed 2 numericals. In the next, let us take some more numericals, interesting numericals based on this de Broglie theory. Okay.